Okay, here we go. Back to business.
And distances that would involve sine theta and cos theta, that leads to lousy formulas compared to linear algebra. The formula that we want comes out nicely. And what do we know? We know that P, this projection, is some multiple of A, right? It's on that line. So we know it's in that one-dimensional subspace. It's some multiple, let me call that multiple x, of A. So really, it's that number x I'd like to find. So this is going to be simple in 1D. So let's just carry it through and then see how it goes in high dimension. Okay, the key fact is, so the key to everything is that perpendicular. The fact that A is perpendicular to E, which is B minus A x, XA. I don't care if that's XA. That equals 0. You see that as the central equation? That's saying that this A is perpendicular to this correction. That's going to...
Okay, not sure if I got it right. Let's write it down first. AT times B minus XA equals 0. XA is B. B minus B is E. AT, okay, understandable. AT times E equals 0. Because it's orthogonal, because they are orthogonal to each other. And E equals B minus XA.
Tell us what x is. Let me just raise the board and simplify that, and out will come x. Okay. So if I simplify that, let's see, I'll move one term to one side, the other term will be on the other side. It looks to me like x times A transpose A is equal to A transpose B. Right? I have A transpose B as one term, A transpose A is the other. So right away, here's my A transpose A, but it's just a number now. And I divide by it, and I get the answer. X is
A transposed A. Yes, it is a number, because A is a vector. So you're multiplying the row vector by the column vector, and what you receive is a number. I think I need to write it explicitly.
A transpose B over A transpose A. And P, the projection I wanted, is that's the right multiple.
But wait, A transpose B is a number too, so they're both numbers. Oh, this is only logical because x is a number, and we need a number to come out from this division, so both numerator and denominator should be numbers here, not vectors.
That's got a cosine theta built in, but we don't need to look at angles. We've just got vectors here. And the projection is P is A times that x. Or x times that A. But I'm really going to, eventually I'm going to want that x coming on the right-hand side. So you see that I've got two of the three formulas already right here. I've got the equation, that's the equation that leads me to the answer. Here's the answer for x, and here's the projection. Okay, can I add just one more thing to this one-dimensional problem? One more, like, lift it up into linear algebra, into matrices. Here's the last thing I want to do, but don't forget those formulas. A transpose B over A transpose A. Actually, let's look at that for a moment first. Suppose, and A, well then, let me take this next step. So P is A times X. So can I write that then? P is A times this number, A transpose B over A transpose A. That's our projection. Can I ask a couple of questions about it, just while we digest that formula? Suppose B is doubled. Suppose I change B to 2B. What happens to the projection?
We multiply by 2.
So suppose instead of that vector B that I drew on the board, make it 2B, twice as long. What's the projection?
Oh, no, yeah,
now?
exactly. 2B.
It's doubled 2, right?
Yes.
It's going to be twice as far. If B goes twice as far, the projection will go twice as far. And you see it there. If I put in an extra factor 2, then P's got that factor 2. Now, what about if I double A? What if I double the vector A that I'm projecting onto?
It won't change.
What changes?
Nothing.
No, the projection doesn't change at all, right? Because the line didn't change. If I double A or I take minus A, it's still that same line. The projection's still in the same place. And of course, if I double A, I get a 4 up above, and I get an extra 4 below. They cancel out, and the projection is the same. Okay. So really, I want to look at this as the projection there's a matrix here. The projection is carried out by some matrix that I'm going to call the projection matrix. And in other words, the projection is some matrix that acts on this guy B and produces the projection. The projection P is the projection matrix acting on whatever the input is. The input is B, the projection matrix is P. Okay, actually you can tell me right away what this projection matrix is. So this is a pretty interesting matrix. What matrix is multiplying B? I'm just from my formula, I see what P is. A transpose above, and I see A transpose A below. And those don't cancel. That's not 1, right? That's a matrix. Because down here, the A transpose A, that's just a number.
Still very rusty when it comes to the rules of matrix multiplication, division, stuff like that. So stuff like associativity and commutativity and stuff like that. I'm still very, very rusty.
Transpose A, that's the length of A squared. And up above is a column times a row. Column times a row is a matrix. So this is a full-scale n by n matrix if I'm in n dimensions. And it's kind of an interesting one. And it's the one which, if I multiply by B, then I get this. You see, once again, I'm putting parentheses in different places. I'm putting the parentheses like there. I'm saying, okay, that's really the matrix that produces this projection. Okay. Now, tell me, all right, what are the properties of that matrix? I'm just using letters here, A and B. I could put in numbers, but I think for once it's clearer with letters because all formulas are simple. A transpose B over A transpose A. That's the number that multiplies the A. And then I see, wait a minute, there's a matrix here. And what's the rank of that matrix, by the way? What's the rank of that matrix? Yeah, let me just ask you about that matrix, which looks a little strange. A transpose over this number, but
it's symmetric.
Well, I could ask you its column space. Yeah.
Okay. What's this matrix? It's basically A times A transposed divided by some number, because A transposed times A is a number, it's not a matrix. So the matrix is actually in the numerator, and the denominator just divides all the coefficients. And since we know that A times A transposed is a symmetric matrix, what can we tell about symmetric matrices in terms of their rank? What is their column space? This is a rank 1 matrix. Am I correct? This is a combination. So A times A transposed is what? It's a combination of rows, correct? No, it cannot be that. It's going to be n by n. It's definitely rank 1. What about its column space? Let's write it now. It's hard reasoning about matrices and vectors and stuff like that just in your head. I guess I'm not good enough for that. We're going to resort to the pen and paper on every occasion. So we have some kind of an A matrix times A transposed 2, 3 times going to be 1 times 1, 2, 3. Yes, exactly. 2 times 1, 2, 3. This is absolutely a rank 1 matrix. Okay, so the column space, the basis for the column space is basically A. So the column space is actually A and multiples of A.
Let me ask you, column. So what's the column space of a matrix? It's if you multiply that matrix by anything, you always get in the column space, right? The column space of a matrix is when you multiply any vector by that matrix, any vector B, by the matrix, you always land in the column space. That's what column spaces work. Now, what space do we always land in? What's the column space of, what's the result when I multiply this any vector B by my matrix? So I have P times B. Where am I? I'm on that line, right? The column space. So here are facts about this matrix. The column space.
Okay, I completely lost that. Again.
That's what column space is. You always land in the column space. When you multiply any vector by that matrix, any vector B, by the matrix, you always land in the column space.
Why? Because we can talk about the matrix multiplication of matrix by the vector, or like Professor Strang here says, it's the other way around, with the vector by the matrix. we can always talk about this as a combination of the columns of the matrix. So whatever the combination of the columns of the matrix, it still lies in the column space.
That's what
This is exactly why when we were talking about the solutions to the equations ax equals b, we can tell that it has a solution when b is in the column space of a, because if it's not in the column space of b, that there is no such combination, which is represented by this vector x, to actually produce this b by multiplying x and the original matrix.
column spaces work. Now, what space do we always land in? What's the column space of, what's the result when I multiply this any vector b by my matrix? So I have p times b.
I'm still in the column space.
Where am I?
In the column space.
I'm on that line.
Yes, and I understand why he's talking about that, because as I've just devised the paper and the other notebook, that the column space of the matrix P, and this is what actually he's probably going to, that the column space of this matrix P, the projection matrix, is A. It's a basis for the column space. So any vector in the column space is a multiples of A. And this is exactly what has to happen, because when we are talking about the projection of B onto A, the projection must lie on A and thus be in this column space. It must be a multiple of A.
Right? The column space.
No, it's actually...
So here are facts about this matrix.
Okay.
The column space of P of this projection matrix is the line through A. And the rank of this matrix is, you can all say it at once, 1. Right. The rank is 1. This is a...
Okay, I need to actually write all this down. So I'm writing what is the column space of P. P times B is always in the column space of P. Also,